class. Now we will talk about the blade design and cascade theory. Here our major motive is towards the flow through a cascade. Then we will try to understand what are the different experimental facilities which are used for this kind of analysis, what are the types of measurements which would be done, and then what are the types of blade profiles, how measurements are done on the blade profiles, and what are the types of the parameters generally which are studied for the effect. These are the things, and then there will be certain analysis related to forces. So we will move ahead, and then we will first understand what do we mean by cascade. Cascade is defined as a row of blades which represents the blade ring of a actual turbo machine. Then if this blade ring is straight or these blades are arranged in straight manner, then this is called as rectilinear or straight cascade. If blades are arranged in annular manner, then it is called as annular cascade. In case of annular cascade, it can be inward flow or outward flow depending upon the direction of the flow. Then why we should study cascade? Why we should study cascade flow? There are some set of facilities where the blades arranged will be kept, and then the flow through such blades would be analyzed. But then why it is desirable, required and essential to study the cascade? So first thing, why it is essential, since it gives us idea about flow physics through blade rows. Secondly, it helps to understand effect of different parameters of flow or geometry. Actually, we know that the flow variables are like velocity, density, viscosity, or there can be temperature as well. So these flow variables can change as per the flow, and hence its effect on the turbo machine needs to be analyzed, and so for that this flow through cascade would help. Further, there can be different types of spacings between the blades, there can be different dimensions of the blades, there can be different profiles of the blades, and then those would also affect the performance of a turbo machine, and hence flow through cascade helps us to get these details where we can study the effect of different flow parameters and also the geometry. As we know, we have seen the one-dimensional flow. So what was the idea in one-dimensional flow? We have seen this. We have drawn the velocity triangle circle also, where suppose I consider the compressor, then in case of compressor we have seen that this will be the rotor, and for the rotor this was the velocity, and then this is the axial velocity. So alpha 1 was the angle, so this was the status, and then it was rotating in this direction. Then we had drawn the velocity triangle like this in case of the compressor, where this was C1, this was CA, this was V1, so this would be CW1, and this complete would be U. Similarly, at the outlet we drew the velocity triangles like this, where this was C2, this was CA2, this was V2, and then we knew angles as alpha 1, beta 1, alpha 2, beta 2. So this was CW2 and this was U2. Here we made certain assumptions which actually are based on the fact that flow is one dimensional. So here we assumed flow is uniform in the passage between the two blades. This is a blade, this is a blade, and this is a passage. So in this passage we assume that flow is uniform. Secondly, we considered only streamwise variation in flow properties. Is considered. Then third, it was only one velocity triangle at inlet and outlet is used to analyze. Thus, having said this, it gives quick estimate. These assumptions are very much helpful for finding out the basic fundamental parameters or performance parameters of a turbo machine quickly. So these assumptions were helpful for us, but now with this improvement from one chapter to other, we are trying to find out what would be the further improvement in the analysis if we try to find out the limitations of one dimensional assumption. So there are certain limitations where we know that there is boundary layer. This is the blade profile, and on the blade profile there is boundary layer. So flow will have zero velocity on the blade. If blade is stationary, it's like a stator blade, and if blade is rotating, then it will gain the velocity of the blade. So there is boundary layer, and this boundary layer will have variation in velocity in the normal direction. So further there can be boundary layer separation. So boundary layer, vortices, separation would exist for flow over a blade. Hence, there is velocity variation in streamwise and also cross stream direction. Further, as we have said, this is the spacing between the blades, and then this spacing would also change the flow pattern. So if we are saying this as spacing between the blades, which is also called as pitch, this distance is called as L, which is a chord length, So this is chord length of a blade, this is pitch. So if we change this, then also there will be change in flow properties. So flow depends upon on the geometry and arrangement of the blades. Therefore, it is essential to consider the multidimensionality. So, considering these three limitations, we are moving from one-dimensional assumption to two-dimensional assumption, where we are considering the variation across the blade passage also. However, a real blade would be three-dimensional, where there will be variation along the height of the blade also. But for the sake of simplicity, we are considering variation only in the passage and along with the variation in the streamwise direction. Here, hence 2D assumption is made, and this 2D assumption is very much suitable for high hub to tip ratio blades. If blade height is more, then what will happen? The variation in the blade direction or blade height along the blade height will be minimal, and hence there will be major variation in the passage itself. So the 2D assumption is more valid for such kind of situation, but this gives us improved estimate than the first or one dimensional assumption. Now the facility which will be used for testing such things is called as cascade tunnel. So if we see a cascade tunnel, then the cascade tunnel would look like this, where there can be many ways by which a cascade tunnel can be made, but integral part of a cascade tunnel is a vane tunnel. Vane tunnel is required in a cascade tunnel so as to create a blow or flow of air over the blades, and hence as there can be different types of wind tunnels, there can be different types of cascade tunnels. Among those, what we are trying to draw here is the one which is blower type of cascade tunnel, where firstly the drive of the air would be created using the blower, and then the part of the tunnel would continue, and in the tunnel, as we know, there are different parts. The same different parts can be seen here as well, and but the difference would be in the test section of the wind tunnel. In a wind tunnel, we would have test sections where models will be mounted, but in this case we would not have a model mounted in the test section. We would have our cascade mounted at the end. So this is cascade or row of a blade, and then this is called as blower, and then this blower is allowing air to enter and flow into the tunnel. In this tunnel, this is conical section, and it is practically a diffuser, since we are talking about low speed subsonic wind tunnel or cascade tunnel. And then we have settling chamber, after the settling chamber we have honeycomb section or chamber. Then we have contraction. This is test section. So these are the parts of a cascade tunnel. So here, as said, this cascade tunnel would start with a blower. Blower would start the air letting in to the tunnel. Then from the conical diffuser, the air will reduce its velocity and it would further become less in the settling chamber. Then air would pass over the honeycomb kind of flow straighteners and wire meshes such that the turbulence level would be decreased or desired turbulence level can be attained, and further these flow straighteners would let the air pass from the contraction section, which would accelerate the air and make it further more uniform in one direction, which will finally pass into the test section and then over the cascade. So here test section receives ultimately uniform air which is going to flow over the cascade. Some essential points of the cascade tunnel include that we need large number of long blades so as to have two-dimensional assumption, but practically it has been seen that 7 blades with h by L, h is the height, L is the chord of the blade, equal to 3, which is also called as aspect ratio, are sufficient. This is the minimum requirement which is required. And then we have these tunnel blades, or the tunnel can be wooden, and blades can be wooden, then can be from the aluminum or can be resin or glass wool. Blades are generally made hollow. Blades are made hollow to accommodate different instruments. Further, what we have seen that this contraction, after the contraction there is test section, and then we want a uniform flow in the test section which would flow over the cascade, but this contraction would have a boundary layer where flow would have variation in the direction normal to it, and this boundary layer is going to enter into the test section. So as to avoid this flow of boundary layer or retarded or low energy flow into the boundary layer, in general porous walls are kept are used to eliminate the boundary layer entering in. Then what we try to measure is velocity basically magnitude, then velocity direction, and these measurements are done for the velocity. We can do the measurement, we can also do the measurement for the total pressure or pressure before and after the cascade. We will do the measurement of velocity before the cascade and after the cascade. Similarly, for pressure measurement, we can do it before and after the cascade. So traverse are placed so as to measure these parameters. Further, in the cascade, the blades would be having instrumentation, and such instrumented blades would measure pressure over the blades. So these are the general arrangements which are done in case of a cascade tunnel. So if we try to see, then we can see that special arrangement in the test section is like this, where we have this part as test section, and we know that this is called as cascade, and here we would see this is an upstream traverse probe. So this probe would have sensors mounted before the cascade. So for this is the velocity, which is Cx1. This is the flow velocity, which is C1, and this is the axial velocity for the cascade, Cx1. And then after the cascade also, flow would come out as Cx2, and then there would be some velocity Cy2, and then this is absolute velocity C2. Then here, like upstream traversing probe, and then likewise there will be downstream traversing probe as well, which would measure all the necessary parameters after the cascade. This would be there in an enclosure, so it is called as downstream traversing probe. And here we will see that this would be called as instrumented blade. So these are the arrangements. So for a blade, if I see, then this is the arrangement. In case of a turbine cascade, this would be the arrangement, and hence here this side of the blade profile is called as pressure surface, and this side is called as suction surface. Suction surface would have lower pressure than the pressure surface. So force would act from the pressure surface to the suction surface. So the instrumented blade, if we try to plot, then this would be a typical instrumented blade, which is hollow, and then this curved line which is passing from the center is called as a camber line. we would see terminologies of aerofoil latter, and then this is called as suction surface or suction side, and this is called as pressure side. And what do we mean by instrumented? This blade would have different holes from where pressure measurement can be done. These will be connected to the manometers which would measure the pressure at those locations. So this is static pressure probe. And if we plot pressure versus x by L, where this length is called as L and then this is x direction. So we would have certain variation and this is x by L is equal to 1. So if we mount the pressure probes on the blade profile, then we can get a variation like this for a typical blade what is shown. Then we know that we told that we can do the measurement of velocity direction, and for measurement of velocity direction there are sensors which are called as yaw-meters. So typical yaw-meter would look like this, which is practically a manometer, but it is used for the measurement of direction of velocity. Here we would have two prongs, if we see its top view in a section, then we can see that there are two holes, and those two holes are basically connected to two tubes, and those two tubes are connected to manometers. And then for the sake of simplicity we can say that it is U-tube manometer. And here these two holes are at certain angle, and this angle is theta. Here this yaw-meter is called as cylindrical yaw-meter, and this cylindrical yaw-meter would be rotated such that there will be balance of the pressure measured by two static probes, and then those two static probes, once they measure the same pressure, then this bisection of this angle would be felt as the angle of the velocity vector. Like this, there is one more yaw-meter, and that yaw-meter is called as claw type of yaw-meter, where again there will be two and then the two limbs are connected here as well to the two manometers or to the two limbs of the manometers, and then same way this would also be rotated so that there can be measurement of pressure at different directions. And then here if we see, then we can see that there are internally the tubes and which are connected to the manometers, and those tubes when rotated would measure differential pressures in each limb, but when this particular orientation is reached, they will measure the same pressure such that the difference is negligible, and from their orientation we can find out the direction of velocity. Then we will go ahead and talk about the cascade performance. Here exit air angle and total pressure loss are the measures. We know that mass flow rate is equal to m dot. If we consider mass flow rate through a cascade, that means through a blade passage, we can say it is equal to 0 to x is equal to s, which is the blade passage between the two blades. S is the pitch, so rho cx dy. This is for unit height of the blade. So we will have dm dot is equal to rho cx dy. So we can apply tangential momentum, which is my in the direction y, 0 to x, cy dm dot, so which is equal to 0 to I cy rho cx dy, 0 to s. So it is equal to rho cx cy into dy. If we apply axial momentum, then we can get mx is equal to 0 to x, 0 to s cx dm dot. Then we have cx rho cx dy, so it is equal to rho cx square dy square. So this integration we are doing in the blade passage. We are not saying that there is only one velocity which is existing and it is uniform. So that we are not saying. We can draw the velocity triangle at different locations, since velocity is varying in different location in the passage, and this is integrated over the passage to get the complete variation accommodated. So we know that mean value of air angle is equal to alpha 2 at exit is equal to tan inverse my divided by mx. So we have tan of alpha 2 bar is equal to rho cx cy dy divided by rho cx square dy. This is the expression for air exit angle. Then we can find out integrated value of delta P naught, which is total pressure loss, and it is 0 to S P naught 1 minus P naught 2, since we are talking about loss in total pressure between entry and exit of the blade. So entry will have higher total pressure, exit would have lower. So it is P01 minus P02 into dm dot divided by integration dm dot. So we have 0 to S P2 minus P1 into rho Cx dy, that is dm dot, and divided by integration rho Cx dy. So these two expressions for one dimensional flow where tan alpha 2 is equal to Cy by Cx and delta P naught is equal to P1 minus P naught 1 minus P naught. So here we can take P naught 1 to be constant, and then that P naught 1 can be coming out from the expression where we would have expression now for integrated delta P naught is P naught 1 minus P naught 2 rho Cx dy divided by 0 to S rho Cx dy. So this is how we can find out the major required quantities, which are like blade exit velocity and the total pressure loss. How to use the different variables effectively. So what are the corresponding terminologies in a cascade, how to implement them for turbine and compressor to find out the forces acting on the cascade. We will see those things in the upcoming classes. Thank you.